Okay, so where did we stop? Like, so we looked at the vanishing gradient problem in training deep neural networks, and like we looked at our first solution, which was this idea of greedy layer-wise training, right? So, and we also discussed how this idea of greedy layer-wise training is not solving the problem, but is actually bypassing the problem by just having a good initialization instead of a random initialization, right? Like, so now how can we really solve the problem, right? So now there are a couple of other solutions that I wanted to talk about. The second solution is to just change our activation function so that we don't have vanishing gradients anymore, okay? Now, the activation function that we are going to see today is called rectified linear units, okay, or ReLU, which is one of the most common activation function that you would see people using with neural networks. It is a really simple function. So f of x is given by max of 0, x. Okay. So the graphical representation for this activation function is like you just it is 0 for all the negative values, and it is a linear line. It's a line for the positive side. Is that clear? Now, the gradient for this function is going to be 0 if x is less than 0, and it is going to be 1 if x is greater than 0. Okay, so as long as these units are activated, you have a gradient of 1, which means you are not at all shrinking anything, right? So now you should be able to train very deep networks because you are not having this shrinking problem, right? So the hidden unit activations are either 0 or positive, right? So in some sense, ReLU activation gives you sparse representations, like because it cannot have negative values. It's going to be either 0 or some positive value. Like whenever it zeroes out, then you have lesser number of activated units. Is that clear? Now, this seems like a simple fix, right? Like instead of the costly greedy layer-wise training procedure, I could just change my activation function. Like if you're using PyTorch, then this is just a matter of changing your activation from like whatever, like sigmoid to ReLU, right? Now, there's one issue with ReLU though. Like, so the issue is, let's say a unit receives a negative value, then you're going to get an output of 0, right? And its gradient is also 0. So it might actually get stuck with 0 output for a while. And it might even just die out, in the sense it is going to be permanently turned off to be 0. Okay, so often many units could die like this, which means you might have issues because of ReLU, right? So how do we avoid this? Like, so the solution is really simple. Like, so we're going to consider a modification to ReLU, which is known as leaky ReLU. Okay, but the idea is whenever things are negative, instead of giving a 0 value, you're going to leak some information, like a small amount, okay, controlled by some epsilon. So f of x is given by max of epsilon x comma x. Is that clear? Where epsilon could be anything, like for example 0.01, some small value. Okay, so this is how leaky ReLU would look like. So we can use the same picture but just change the color. So leaky ReLU is going to be behaving exactly like ReLU for the positive side, but for the negative side, you're going to have a small leaking from the negative side. Is that clear? Now, there is always some small value, right? Like there is no 0 gradient. So in that sense, leaky ReLU will not die. So it will always pass some gradient. So you can figure out like what to do with that, right? Like, so now this ReLU activation function can help us to train very deep neural networks without any pre-training. Is that clear? Any questions about ReLU? No questions? Okay, now the third solution. okay, is the idea of batch normalization, which is kind of related to scaling the gradients, but not exactly the same, okay. Now this was proposed by Ayof and Shekji 2014, okay. Again, this is one of the famous tricks that we have developed in the last decade, okay. So you can train really deep neural networks with batch normalization, okay. But what is the idea for batch normalization? So one of the main reasons why gradients saturate is because the sigmoid unit that you are having, right? So the unit saturates, okay? So you have a sigmoid, okay? If your output goes either very close to 1 or very close to 0, you get 0 gradient. Is that clear? So when your activation saturates, your output, like when your output activation saturates, like then the gradients also go close to 0. Okay, so in sigmoid case, like if the output goes to either close to 0 or 1, then sigma dash goes close to 0. And the same goes for tan H as well. Okay, now the idea of batch normalization is to take your pre-activation, okay, and normalize it in such a way that your unit always operates in this region. Okay, you try to reduce the value of pre-activation. Okay, so what is pre-activation? Like, let's say I have sigma of Wx plus B. Okay, I'm going to take this Wx plus B. If this value is very high, then I'm going to go close to 1. If this value is very small, I'm going to go close to 0, right? So I'm right. I'm going to take this value and normalize this value by using this batch normalization trick, okay? I haven't told you what is batch normalization trick, but the idea is you take this and add batch normalization here. That is going to take care of avoiding saturations. Is that clear? So how am I going to do that? Again, a simple trick. So the input for batch normalization is some pre-activation. It takes Wx plus B as input, okay? So some pre-activation, let us just call that as X, okay? Over a mini batch. B is equal to X1 to Xm. Is that clear? Now this batch normalization layer is going to have 2 parameters that we are going to learn, okay? So the parameters of batch norm are gamma and beta. Is that clear? Now this layer is going to take xi as input with some parameters gamma and beta produce yi, which is the output. Okay, this is my output. So how am I going to do that? So I'll take this bunch of pre-activations. I'll first compute the mean and variance. I'm really doing standardization here, okay? So mu b is given by 1 over m, summation I is equal to 1 to m xi. Similarly, sigma b square is given by 1 over m, summation I is equal to 1 to m xi minus mu b the whole square. So this is the mini batch mean and mini batch variance, right? So once I have the mini batch mean and variance, I can normalize by xi, which is the normalized pre-activation, is given by, you take the original pre-activation, you subtract the mean, divide by the variance. Okay, this is basically normalization. Is that clear? Now, once you normalize, right, it might be the case that you might hurt the performance of the architecture for some tasks. What if the task really expects you to have big values? So we're going to give that freedom back to the neural network by taking this xi bar and scaling it with gamma and beta. So gamma times xi bar plus beta. Okay, so we are doing scale and shift, which is the opposite of subtracting by mean and dividing by variance. Is that clear? Now, this is the idea. So now, essentially, you take a mini batch, you compute the mean and variance, subtract the mean, divide by the square root of the variance. Then you also add back by having these parameters. Now, if your network thinks that it needs to denormalize or like do the reverse of normalization, it can do that by using this gamma and beta parameter. Is that clear? Any questions? If the network wants to cancel the normalization effect, it can actually do that by using this. Okay. Now, how do I use batch normalization at test time? At training time, we get a mini batch. We are computing this mean and variance with respect to the mini batch, right? So what will we do at test time? I give you only one example. Any answer in the chat? So I give you only one example. Now you want to compute the mean and variance. M is equal to 1. How would you approximate? No solution. So how do you do this normalization with one example at this time? Okay. But if I give you a batch of test examples, then you can compute the mean and variance from the batch, right? Like, so if I don't give you the batch, so what is the best way to approximate it?
Just use it.
Sorry?
Just use it as is without the.
Oh, then there is no use, right? Like if you remove the normalization, then you're going to saturate. Also, it is not what the model was trained for. Yeah.
The entire data set?
Yeah, you could just approximate it from the training set, right? Like, so from the entire data set, like you could compute the batch mean and variance, like which could be your, or you could have a running average during training time, right? Like, so which could be a proxy when you're doing test time performance with just one example. Is that clear? So any questions about the solutions? Yeah.
The parameters of scale and shift all those, well, they can take any value. What is the need of normalizing before?
Okay, that's a good question. So what is the purpose of normalization when we are scaling and shifting? Okay. So in theory, we don't want to affect the expressive power of the network, right? So like if you always normalize without scale and shift, then you have a restrictive class of neural network, which can only model a certain set of functions, right? Like, so you want the flexibility. So you're giving back that flexibility by using gamma and beta, okay? However, when you do backpropagation, like on gradient descent, like since you're starting with a good initialization, the model has no incentive to rescale unless it is actually required by the task. So in practice, it should work well. Okay, any other questions? Okay, so I think that concludes our discussion on deep neural networks. So now we're going to change the order a little bit so that it is more useful for your Kaggle computation. I wanted to talk about optimization, but we are going to do it in the next week. But for the rest of this lecture, we are going to look at a very specific neural network architecture, which is going to be useful for image data. Okay, so which is the idea of using convolutional networks. Okay, so far, all the algorithms that we have seen, including simple models to neural networks, right? So they were always taking a vector as an input, right? Like, so you will pass a vector. It could be logistic regression, or it could be SVM, or it could be the one-layer neural network or deep neural network. We were always passing a vector as input, right? Now, in your third assignment, when you were doing the document classification, like or text classification, like you had a bunch of words and you constructed a vector from that word to begin with, right? So that is for text. Now, what can we do for images? Now, let's take a standard ImageNet, like say image classification task. Okay, so this is called C410 data set. Okay, well, it's really low quality because it is just 32 cross 32 pixels. Okay, so this is a 10 class problem. Okay, so I have a bunch of classes here, like airplane, automobile, bird, cat, and so on. And for each of these problems, I have a bunch of examples. Okay, and these examples are colored images. Now they are going to be 32 cross 3 images. Okay, so we are 32. The first 32 is the height of the image, and this is the width of the image, and this 3 is the RGB color channel. Okay, now this input is not a vector, right? It's actually a complex tensor. Like it has it's a 3-dimensional matrix, right? Like so. Now, first question. So how would we pass this 32 cross 32 cross 3 input image as an input to, let's say, fully connected feed-forward network? Yeah.
You can try to vectorize it.
Yeah, you can vectorize it, right? Like so, you take this and create this one long vector, which is of the size 32 cross 32 cross 3. I don't know what that number is. Okay, I have the number. So it's a 3072 size vector, and then you pass it to this neural network. Okay, now let us try to understand like what such a neural network can do and cannot do. Okay, so here is the neural network. It is going to take all these pixels somehow vectorized. Okay, so you have 3072 pixels. So that is fed, and you have some hidden layer, let's say a bunch of hidden layer, and then you have a 10 class prediction. Is that clear? Now, the first, let's say that for the sake of our discussion, there are 100 units in the hidden layer. Okay. Now, so the first observation is each of these units in the hidden layer is connected to 3072 units in the first layer, right? So you have a weight matrix here, which is of the size 3072 cross 100. Okay. Now, well, it's not a lot. It sounds like a reasonable number. But remember that this is a very, very, very low quality picture. It's just 32 cross 32. Okay. Now imagine you have a 200 cross 200 pixel picture, which is also not very high quality. So nowadays we have like, I don't know, 1K, 2K, or whatever, like higher number of features, so like pixels, right? Like so. Now even if you have a 200 cross 200, okay, so then you have 200 cross 200 cross 3, which means each unit is going to have 120K weight multiplied by 100. Okay. Now you can see the problem. So if you take the image and do this naive vectorization and pass it through the neural network layer, you're going to have a huge number of parameters just in the first layer. Now think about the second layer. Let's say it goes from 100 to 500 even. Okay, this is a very small matrix when compared to the first layer matrix. Okay, so majority of the parameters of this network is going to be concentrated on the first layer. Okay, and this could lead to overfitting because it is just way too many. Is that clear? Now, even though we have majority of the parameters in the first layer, they are not really exploiting the fact that this is an image. Because in an image, we know that neighboring pixels matter, right? So if you want to identify like for example, a face of a human, then it is important to know that, okay, there is an eye, there is another eye next to it, and there is a nose like in the bottom of it, right? The spatial location of the pixels matter. Now, that information is completely lost in this vector representation. Because we know that there is no ordering here, right? Like you can just shuffle this and you're going to still have the same representation, right? Because there is no notion of neighbors or relatedness in a fully connected architecture, right? Now, somehow we need to take advantage of the fact that these are images and there is a spatial structure. Okay, first goal. The second goal is to reduce the number of parameters, really. Like we don't want this many parameters. So how do we do that, right? Like, so to do that, we are going to look at a specific variation of neural network, which is the idea of convolutional networks. We are just going to call that as ConNets from now on. Okay, now in ConNet, each neuron is going to be arranged in 3 dimensions. Okay, it's not going to be a flat vectors anymore. So each neuron is going to have 3 dimensions, like width, height, and depth. Okay, and each layer is going to take a 3D volume as input and output a 3D volume again. If you think about a neural network layer, like a vanilla layer, it is going to take a vector as input and produce a vector as output, right? Now, instead of that, we are going to take a 3D volume as input, like 32 cross 32 cross 3, and we are going to produce another 3D layer as output. Is that clear? Now, you can see the difference here. In the left side, we have our regular neural network, okay? So this regular neural network takes a vector as input and produces a vector. Again, take vector as input and produces a vector, right? On the other hand, we haven't seen what is inside the convolutional network, but these are convolutional layers, okay? You can see that the first layer takes 32 cross 32 cross 3, a 3D volume, and it produces another 3D volume. Then there is another 3D volume. Finally, you produce, if you have a 10 class problem, you have 1 cross 1 cross 10 as the output. Is that clear? Now, if you just zoom into one of these volumes, you have the depth, height, and width. Is that clear? So, any questions? Okay, so now let us talk about how to construct these 3D layers, which takes 3D volume as input and 3D volume as output, right? Like, so we're going to call these layers as convolutional layers. Okay, now convolutional layers are going to have a set of learnable filters. Okay, I'm going to learn a bunch of filter in the layer. Now these filters are going to have a small width and height when compared to the original image. Okay, so for example, I can take a 32 cross 32 cross 3 image and I pass it through my convolutional layer, conv layer. Okay, now this conv layer is going to have a bunch of filters. Okay, now each filter could be something like 5 cross 5 cross 3. So what does this mean? My original image was 32 cross 32 cross 3. Okay, if I have to draw it pictorially, it's going to look something like this. 3 matrices of size 32 cross 32 cross 3. Okay, but my filter is going to be a smaller version. So this is 32 32 3, but this is just 5 5 3. Is that clear? So during my forward propagation, I'm going to take this filter and do a dot product with the first part. The second, I'm going to slide over my image, okay? So this is what I'm going to do. Like, so I will first apply my filter for this 5x5x3. Okay, I can do a complete dot product and some things together. I'm going to get one value. Like, is that clear? Now, I'm going to move my window little bit. Okay, so for example, I could move my window by 1 pixel, which means I will start from the second pixel and go up to, sorry, I'll start from the second pixel and go up to the 6th pixel. Okay, I'll do a dot product of my filter with this particular patch of the image. I get one number. Is that clear? Now, finally, like I would compress the whole thing into just one smaller matrix where each value corresponds to the dot product between my filter and the input, right? Now I can have many filters like this. Like if I have 5 filters, then I will get 5 such matrices. Okay, so that's why my output is like a 3D volume. Is that clear? Now, there are a lot of questions here. First of all, what are these filters? Right, like so these filters are essentially replacing my parameters W. Okay, I'm going to learn these 5x5x3 numbers. Okay, now one intuitive way to understand filters is each filter is trying to detect some like structure in the image. Okay, so for example, I could have an eye filter which is just looking for eye in the image. Okay, so let's take an example image, like a hypothetical example. Now, let's say I have an image like this. Okay, I could have this eye filter, which is a 5x5x3 patch. Okay, it will check whether there's an eye here, whether there is an eye here, whether there is an eye here, whether there is an eye here. Okay, so my filter is going to say 0, 0, 0, 0 because there is no eye. Okay. And it checks here, no eye. It checks here, there is an eye, right? So it can say 0, 1, and probably a 0, another 1, 0, 0, 0, 0. Right? So this filter checks if there is an eye and is 1 whenever there is an eye. Now I could have 100 such features, like one feature looking for eyes, one feature looking for nose, one feature looking for lips. Now my first layer is capturing all these things. Now I can have another layer of convolutional layer, like which is going to combine these things together to detect, let's say it's a face or not. Is that clear? Now, the reason why I'm calling this as a convolutional layer is because this whole idea, right? Like so, doing a dot product and sliding over the thing, right? Like so, it is equivalent to convolution operation. Okay, so when you implement this, you're going to implement this by convolution. Okay. Is that clear? Any question? Yeah.
Don't we lose too much information by applicating those filters? Because if the dimension of the matrix is always too much, isn't it a problem for the next layers of the?
Okay, that's a good question. So the question is, don't we lose a lot of information here? First of all, like, do we agree that we actually keep more information than a fully connected network? Right? Like, so fully connected network loses all the relationships, right? Like, so on the other hand, this is better. Now, the question about the granularity, right? Like, so that is going to be controlled by the number of layers. So the example that I gave you about eyes is hypothetical, okay? Now, in reality, the first layer will detect, we are going to see some examples. Like, so we have the example right here. Maybe, no. I have some example like soon. Like so, we will see that the first layer is going to detect very, very simple concepts like lines, edges, patches, like very, 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 very simple complex, okay? And the next layer is going to combine these concepts together. And the next layer is going to combine these concepts together. Maybe after 4 or 5 layers, you will have eyes. Okay, so you will not lose a lot of information, like because you start with low granularity, right? Like at least when you're learning. Now, okay, so any other question? I want to show. I want to show an animation of how this works. Okay, so this animation is okay. I moved things quickly, so the screen is not working. Okay, while we get back the screen, this is an animation taken from Stanford's CNN course. Like it's one of the famous courses, like dedicated to deep learning for computer vision. Okay, so if you are more interested in like vision, like computer vision, like I highly encourage you to go check the course. But this is a really useful visualization to understand how convolutional layer works. But let us wait for the camera to work so that people in the Zoom can also follow us. Come on. Okay. Yeah, so it is going to come back. People in Zoom, like we are waiting for that. Okay, so now you see the animation. Okay, so let's see what is happening here, right? Like, so I have my first filter, which is a 3x3 filter, okay? You see that you take the first filter and you're doing dot product with every row. You're scanning through the rows, okay? And you're doing dot product, and that is going to give you those values that you're seeing there. There are 2 filters here. So the output volume is going to be 3x3x2, okay? So is this clear? Yeah?
When you're saying dot product, like what does that mean
Okay.
exactly? Because this is like, in the way it's represented here, it doesn't look like
okay.
Exactly.
Okay, let me see if I can pause. Yeah, I can pause. Okay, I paused it. Okay, so what do I mean by that? Now, let us consider this -1 that is highlighted, right? So how is it computed? It is computed by taking this 3x3 and doing a element-wise multiplication with this 3x3. Similarly, taking this 3x3 and element-wise multiplication with this an element-wise multiplication with this. Then you just sum everything and add the bias.
All right, thanks.
Is that clear? So that whole thing is a convolution operation. You convolve around the image. Is that clear? There are still some missing pieces. Like I haven't talked about how to move and like what would be the output structure and so on. But is the higher level idea clear? So your question was about describing?
How does it work with there's filter W0 that W1? How do they add them together to get the...
Oh, no, we are not adding them together. Like, so, like, for example, in this case, W0 computation is happening, right? That is corresponding to this particular thing, okay? So we will do the W2 thing separately. So for every W, you have one map as an output. Is that clear? Any question? Now, so the advantage of, okay, now let me slowly go back to the nodes without hurting the camera. Okay. Now the advantage of having these local filters is the number of parameters is going to be very, very less. Okay. Now imagine you have a 5x5x3 filter. Okay. You can have 100 filters. Now you only have 5x5x3 times 100. You don't have this 120K or like million parameters that you would get with fully connected networks. Okay. So first of all, there is this advantage with respect to the number of parameters. The second advantage is you are looking at this one patch, right? So you are actually giving importance to the spatial structure, which is completely lost in fully connected networks. Is that clear? Now, for example, like when you have a 32 cross 32 cross 3 image and a filter which is only 5 cross 5 receptive field, okay, then the number of weights required for this filter is really 5 cross 3, which is 75 plus 1 for bias, right? On the other hand, like with fully connected network, you need a lot of parameters. Is that clear? Now, there are some pieces which are still missing for you to implement this, okay, which is the idea, like how am I going to move in the figure? Like, so do I move by 1 pixel or 2 pixel, right? Like, so those things needs to be figured out. So the spatial arrangement, okay, is kind of captured by 3 hyperparameters. Okay, so the first hyperparameter is the depth. Okay, so the depth of the output, right, is dependent on how many filters you have. If you have 5 filters, you'll have 5 matrices in the output. If you have 10 filters, you're going to have 10 matrices in the output. Okay, so when I say 5 cross 5 cross, like for example, in the output, when I say 5 cross 10, it just means I have 10 filters. Okay, now what about the height and width of the output, right? Now that is going to be dependent on 2 other factors. One is stride. Okay, so stride basically tells how many pixels to move. When my stride is equal to 1, I will move 1 pixel at a time. When my stride is equal to 2, I will move 2 pixels at a time. Okay, so now you can see how it is useful. Like for example, let us take a simple 4 cross 4 pixel. Okay, and I have a 2 cross 2 filter. When I have a stride of 1, then I will first convolve here, then here, then here. So how many, what is my width? My width is 3, right? So I had 4 elements. After doing my filter, it reduced to 3. Okay, however, if I was using a stride of 2, then it means I will first do this, then I will skip 2 pixels. So I will do this. So I will have only 2 output, right? So by controlling the stride, you can reduce the number of features, like number of entries in the output. Okay, so you can have a smaller output by increasing the stride. Okay, now sometimes, okay, let's imagine, let's go further. Like, so what if stride is 3? So if stride is 3, let's say I will do this. Let's say my stride is 3. Sorry, this is wrong. I'm here. Let's say my stride is 3. Then where do I go? 1, 2, 3. I have to go here, right? So now you see that I cannot do the filter because I am missing this part, right? So whenever you miss parts like this, that is where the third factor comes in, which is the idea of zero padding. Okay, you can add zeros in the column, in the corners. Okay, so that it helps you for, like, it helps you for better finishing your stride. Is that clear? So I think now this completes our description. Now we can actually go back to the visualization again. Okay, okay, it works. So now I'll toggle the movement. Can somebody guess what is the stride here?
2.
Is it written somewhere? No. Okay, good. So it's 2. Now, how many zero padding I have done? So if I do one line of zeros, it is zero padding 1. I can do 2 circles sometimes, like 3 circles sometimes. Okay. So I have done 1 level of zero padding. Okay. But sometimes you also have to do zero. You have, okay, most often you have to do zero padding to make sure you have valid strides. But sometimes you would do zero padding by yourself, even if striding is not a problem, if you want to keep the image bigger. If you want your output to not reduce in size, then you could use zero padding. Is that clear? There are two reasons to use zero padding. Okay, now let's go back to our slide. Okay, so now let F be the receptive field size, okay, which means like whether it is 5 cross 5 or 6 cross 6 or 3 cross 3. Then S be the stride, P is the amount of zero padding, okay, and W is the input volume size. For example, it could be 32 cross 32 cross 3, in which case W is 32. So we are kind of assuming that we are always looking at squares, okay? So that's why I have only one F, one W. Like if you have rectangle, then you might need to have different F and W. Okay. Now, if I give you these four numbers, you can actually calculate what is the output size going to be, okay? The output volume size is going to be given by this formula, W minus F plus 2P by S plus 1. Okay, well, we're not going to discuss how we came up with this formula. You can just use it directly when you are implementing these algorithms. Now, let us imagine I have a 7 cross 7 input and a 3 cross 3 filter, and stride is equal to 1 and padding is equal to 0. Okay, now I can actually compute my output size. It's going to be 7 minus 3 divided by 1 plus 1, right? So it is going to be 4 plus 1, so it's going to be 5. So which means if I start with a 7 cross 7 input, after doing this particular convolutional layer, I'm going to get a 5 cross 5 output. Is that clear? Now, if I just change my stride to, let's say, 2. If S is equal to 2, then I'm going to get 7 minus 3 by 2 plus 1, which is 3 cross 3, right? I think if we do S is equal to 3, it will not work. Then you have to change your zero padding. Is that clear? So here is an example for striding, but in 1 dimension instead of 2 dimension. Okay. So you can see that my input is 5 dimensional. Okay. And my filter is 3 dimensional. So if I have a stride of 1 with zero padding 1, then I will first stride over this, which is what is given by -2, right? Then I will stride over this, which is what is given by 2. Then this, which is given here, this given here, this given here. Is that clear? So if I have a stride of 1, my output is going to be 5 dimensional, like from 5 dimensional, because I use zero padding as well. However, if I have a stride of 2, my output reduces to just 2 dimensional. Is that clear? Any questions? Okay. Now I think we have discussed in detail how the convolutional layer works, right? Like, so the biggest advantage of convolutional layer is like really parameter sharing. Okay. Now imagine you have an input image of size 227 cross 227 cross 3. Okay. Now, if you have a first convolutional layer which has F is equal to 11, S is equal to 4, P is equal to 0, and K is equal to 96 as an example, some random convolutional layer, this is going to have an output of 55 cross 55 cross 96. You can see the reduction in size, right? Now, if you don't use any parameter sharing, okay, so then you're going to have 55 cross 55 cross 96 cross 11 cross 11 cross 3 plus 1 for bias. Okay, so you're going to have approximately 1057056. Okay, so well, exactly. So this many parameters. if you don't use parameter sharing like convolutional layer. However, when you use a convolutional layer, all you are doing is just 96 times 11 cross 11 cross 3 plus a bias of 96. So you're only using approximately 35K parameters. Yeah.
Just out of curiosity, what happens when the input image is not a square?
Okay. It doesn't really matter that much, right? Like, because as long as your filter is square, you can take care of it by adding zero padding. Okay. Yeah.
So here we learn one component of learning is the filters, or they're static.
We're learning the filter.
We're learning.
Oh, that's the whole point. We're learning the filter.
And are we stacking the filters like as deep we go when we fully connect them?
Okay. At some point, we are going to switch to fully connected. I'm going to show you. We are still looking at only first layer. Okay. But I really want to finish this today. So let's just take 5 more minutes extra just for today. Because this is also useful for your Kaggle. Okay, so here is an example of the kind of filters that you would learn in the first layer. You can see that it is mostly either looking at colors or strides or edges or stripes and so on. Right? Is it clear? Now, as a summary of the conv layer, okay, so our conv layer is going to accept an input, which is, let's say, W1 cross H1 cross B as the input, okay. It is going to produce an output, which is W2 cross H2 cross B2, okay. And this conv layer is going to have 4 hyperparameters, okay. The first hyperparameter is the number of filters. They're going to call it K. Then the spatial extent, like F, how big is the stride, like how big is the patch. Then the stride, S. Then the zero padding, P. Is that clear? So I think there is a better summary in the notes. Like I would recommend you to go for like read it in detail. But you have the idea, right? Like, so now this is one layer. Now in a typical convolutional layer, you are also going to see some pooling layers. Okay. Now pooling layers are really simple layers. They don't have any parameters. The only purpose of the pooling layer is to reduce the size. We want to reduce the size as much as possible so that the number of parameters is under control, right? Like so here is an example of a pooling layer. Okay, so this pooling layer takes this image, okay, and it looks at 2 cross 2 filters with strides of 2, and it is basically doing max pooling. So what does that mean? It looks at this 2 cross 2. What is the maximum value here? 6, right? So that is what is here. Then it has a stride of 2. It goes to the next one. What is the maximum value? 8. Here, the maximum value, 3. The maximum value, 4. Okay. Sometimes when you're just using these filters as feature detectors, it is important to see where is the feature, right? So max pooling is sufficient. Okay. Now there are many ways in which people do pooling. Like for example, you could do average pooling, like where you take all these 4 numbers and you compute the average. Okay. Or you could do L2 norm pooling. Like, so you can do a lot of pooling operations. I should say that in the beginning of convolutional neural networks era, people were doing one layer of convnets and another layer of pooling, another layer of convnet, another layer of pooling. Oh, by the way, it is very important that after the convolution, you have a sigmoid or tanh or ReLU nonlinearity. Okay. See, convolution is also a linear operation. It's not a nonlinear operation. So it is very important that after convnet, you have a ReLU or nonlinear or sigmoid or tanh. Then you do pooling if you want. Then another layer of convnet, ReLU, pooling, and so on. Okay. Finally, once you have enough number of layers, your final output is what? It's a if it's a 10 class problem, it's a 10 units, right? So one easy way to do that is just flatten out the final vector. You flatten out the final vector and you pass it through a feed-forward network, and that feed-forward network is going to give you 10 class output. Is that clear? So here is an example architecture. So in this case, it takes an image, it passes through first layer of convolution, then ReLU, then convolution, ReLU, then you do pooling. Okay. So normally people treat this as a block. So you can consider this as one block. Okay. You repeat this block 3 times. Finally, you have a fully connected layer, which is giving you the class probabilities. Okay. So one quick note before I finish is, people used to do pooling like 10 years back. Like, so nowadays, you won't see a lot of pooling operations in convolutional architectures. Like, so because over the years, we have learned that instead of doing pooling to reduce the features, you could just increase the strides and it works fine. So whenever you want to reduce the features, just increase your stride by 1 or 2. You don't need to pool to reduce. Is that clear? Any questions? Yeah.
Can you learn filters on different size? Like, how can you? I can be a different size. So.
Okay, that's a good question. So can we learn filters of different size? Okay, so within a layer, we learn same size filter. That makes it easy to implement the convolution operation. Okay. Also, like if you have different sizes, then you have to handle different sizes by padding and all the other things, right? Like, so normally we learn same size filters in one layer, but you can have different sizes in different layers. For example, like with an image which is 200 cross 200, people would do 11 cross 11 filter in the first layer, then 8 cross 8, then 5 cross 5, then maybe 3 cross 3. So you can do this kind of things, but you cannot change it within the layer. There is also a question in the chat. Okay, I think something I missed in the beginning. But more specific, can layers of the input volume be different? Can the layers of the input volume be different? I don't know what that means. You can have any number of channels in the input, so it doesn't matter. Any other questions in the class? Okay, so, well, one of the reasons why I wanted to finish this today is like now you can actually go and explore using convolutional networks for your Kaggle competition. Okay, so in PyTorch, like for example, you should be able to see, like look at some example convolutional architectures which you could use for your competition. But a very clear warning: when you're using these packages, just make sure you are not using a pre-trained convolutional network. Okay, so if you are using a pre-trained convolutional network, it means that network has been already trained with other data sets, and you have a good set of parameters to start with. That is outside the scope of the competition. If we find that you are using pre-trained convolutional networks, you get a 0 in the competition for the whole competition. Okay, so don't use pre-trained networks like so. You can take the architecture from anywhere, like it's an open competition, right? Like so, you can copy the architecture from anywhere if you want, but make sure that you are not copying the weights. Okay. Okay. So I think we'll stop here. So next week we are going to talk about advanced optimization methods.